Fast radio bursts, or FRBs, are blasts of energy that are brighter than many galaxies. They occur across the universe and their physics still remains a mystery. A team of scientists caught one such FRB last year that was particularly remarkable. It traveled 8 billion years to be detected by the European Southern Observatory's Very Large Telescope. Dr. Stuart Ryder, an Adjunct Fellow with the School of Mathematical and Physical Sciences at the Macquarie University in Sydney, is one of the astrophysicists who has been working on the detection of such FRBs. Dr. Ryder, who wrote a paper in Science, along with Ryan Shannon, a professor at the Swinburne University of Technology in Australia, spoke to Mayank Chhaya Reports about FRBs and what they mean as a frontier science of astrophysics.
Welcome to Mayank Chhaya Reports, Dr. Ryder. It's a great pleasure to have you on.
Thank you very much for having me.
Congratulations on your remarkable findings, your and your teams.
Yeah, no, we're really excited about it, and we think it represents a pretty significant step forward in the ability to make use of these fast radio bursts as probes of our distant universe.
Indeed. It strikes me that when this particular FRB, the fast radio burst, left its source 8 billion years ago, our solar system, our Earth, therefore us, we're still 4 billion years into the future. And by the time it covered half the distance, we were still forming. And now it's here. It's both fascinating and incomprehensible. What was your reaction?
Yeah, well, from the time that we first realized just how distant and how old this burst was, it really set things abuzz. I mean, we talk about the distances to these objects in terms of redshift, which is simply the amount by which space effectively is stretched because of the expansion of the universe. And this particular one had a redshift value of just over 1. And although there's nothing special about that particular number, it just like, it was like getting that sub 4-minute mile. We thought, wow, we've really come a long way just in the last 5 years since we had the ability to pin down the locations of these fast radio bursts, and therefore try and get an estimate for the distance to the host galaxies.
FRBs last barely a few milliseconds. This one was particularly short, I'm told. What happened to you when you first detected it? What exactly did you see?
Yeah, so this particular burst actually lasted less than 1/2 of 1,000th of a second, which is not unusual for these fast radio bursts. Most of them are, a millisecond, as we call it, or even shorter than that. But to me, the incredible thing is that despite traveling through that enormous distance, the pulse, which you would kind of expect to get a little bit spread out by passing through stuff on the way to us, actually barely changed. Obviously, it got stretched by a factor of 2 or so because of the expansion of the universe. And yet, in many other ways, it seemed relatively unaffected by how far it had actually come. But we have a system running on our Australian Square Kilometre Array Pathfinder telescope here in Australia that is constantly searching for these kinds of burst signals or something that could be a fast radio burst, while the telescope is busy making observations of other things in space. And so it's constantly sitting there monitoring, looking out for these things that might be the next most distant fast radio burst. It's simply too much of a job for any one of our team members to be sitting there looking at the data in real time and trying to see if there's a burst there. We are wholly reliant on a lot of computing power. And really that's part of the reason why we didn't even know that fast radio bursts existed just over 15 years ago, because we simply didn't have the technology or the computing power to be able to do these kind of really rapid searches that have to take place.
Oftentimes these are brighter than entire galaxies. This particular FRB seemed to release as much energy as the sun puts out in 30 years. That's impossible to fully comprehend for an ordinary mind.
Well, it is, and that's why one of the big challenges that remains today is to try and work out what kind of object could possibly power or give out that kind of energy in such a short space of time. Well, the first clue is in that very short duration. that means that the object itself can't be truly large in size, because otherwise that signal will get spread out in time. So we have some constraint on the physically larger scale that this thing could be. And here we're talking tens of kilometers or so. So it's incredible. Something that less than the size of a city is able to put out that amount of energy. But of course, it only has to do it for a relatively short amount of time. And so that's why at the moment, the current favored model is that fast radio bursts are emitted by what we call magnetars. Magnetar is simply astronomy jargon for a highly magnetized neutron star, which, as the name implies, that's a star, or actually the remains of the core of a star, which consists purely of neutrons. Gravity has compressed what was left of the star's core after it underwent a supernova explosion, and it now consists purely of neutrons. All the electrons and protons have all been squashed together by the force of gravity to leave just pure neutrons. And we know that these objects exist. We've seen them at other wavelengths in even our own galaxy. And a few extreme cases when they have really, really strong magnetic fields, we believe that effectively is like the battery that would provide the power source. And it's probably something to do with the magnetic field lines around a magnetar getting twisted and eventually snapping and then reattaching. And in that course of doing that, they could release significant amounts of energy, such as a fast radio burst.
How do you explain the fact, like you said, it wasn't that stretched out, notwithstanding that it traveled such a long distance and presumably through a lot of intergalactic material?
That's right. Yeah. So we have seen in a few other fast radio bursts what we call scattering. That is inevitably as the radio wave, because strange thing, these objects are only seen at radio wavelengths, and in fact they don't even fill the entire part of the radio spectrum. And so that's another clue as to what causes them, but we haven't cracked that one yet either. But in the course of passing through this gas and free electrons and other things in the space between galaxies, it's not unusual for some of the radiation to be scattered and in effect become spread out in wavelength space. And we can use that obviously to tell us a bit about the nature of the material that it passed through. And the most useful measurement of all actually is what we call the dispersion measure. And that comes about from the fact that the lower radio frequencies actually arrive later than the higher radio frequencies because of passing by free electrons in space. And the more of these free electrons that they intercept, the more that stretching towards lower frequencies becomes. So one of the most powerful things about a fast radio burst is that just by detecting it and measuring the amount of that dispersion, we already know straight away roughly how far it had traveled, because the more space that it's been through, the more distant its host galaxy, the more that dispersion will be. However, there are other factors that can come in and introduce spurious extra dispersion that are not to do with the stuff between the galaxies. And so that's one of the factors that we still need to account for. And so if we want to know how far the burst has traveled, the only sure way to do that is to get the distance to its host galaxy. And for that, we need to make observations with very large optical infrared telescopes on the ground to measure their spectrum and look for that redshift, because that's a pretty solid indication of just how far the burst had to travel.
This is perhaps a silly question, but these signals, do they ever die completely? Because 8 billion years, it's still there. We are catching it. Presumably, it's gone further away. It's somewhere in the universe still. So is that the natural state of affairs, that these things just don't die? They become feeble, maybe perhaps over a time?
They will, yeah. This is the inevitability of the inverse square law of radiation, that as the object fills more and more space, travels further, that the surface density of radiation becomes less and less. So yes, eventually it wouldn't have been detectable if if it travelled much further. In fact, this particular burst, based on what we know about our telescope system, we'd be lucky at the moment to be able to detect one significantly more distant than this one. But we are in the process of upgrading our telescope systems to enable us to push a little bit further in terms of distance and to even fainter bursts. Because the worry is that we're only picking up what we call like the tip of the iceberg.
Right.
And we'd really like to understand what is the whole range of energies that these fast radio bursts put out. Because it's pretty clear that they're not a constant beacon, if you like, not like what we call type 1a supernovae, which is one way that people have used, or the primary way for a number of years that people have been using to infer that the expansion of our universe is actually accelerating. So in some ways, fast radio bursts are not very good distance indicators, despite having this dispersion measure attached to them. But in fact, it turns out if we find enough of them over a large enough distance range, we think we can actually begin to use them to try and narrow down the range of what's called the Hubble constant. That is the amount by which the universe expands with time. And there's quite a bit of a controversy raging right now, and that the type 1a supernovae give one value for the Hubble constant, and that's not compatible with a different value that's given by the measurements of the cosmic microwave background. So we think fast radio bursts might actually be a powerful but independent probe that hopefully might settle that dispute as to what the real value of the Hubble constant is.
Aren't there any magnetars either in our galaxy or in our immediate neighborhood?
There are, and in fact, one of the best clues as to what fast radio bursts might be came back in 2020 when a known magnetar in our own Milky Way galaxy, so obviously a lot closer than this one, was seen to emit at radio wavelengths pulses of energy, in fact more than one, which were quite reminiscent of what we see in fast radio bursts. However, these bursts were much, much lower in energy, so maybe it's the low energy end of the range of fast radio bursts. But one of the more fascinating things about that particular object when it burst is it was also detected at X-ray wavelengths. And that's something that's never happened for any other fast radio bursts. We've never seen, apart from pulses of emission in the radio, we've never seen similar pulses at any other wavelength, whether it be optical or gamma rays or ultraviolet or anything like that. And so this was the first hint that maybe if this object we saw in our own Milky Way galaxy, the magnetar, if it can put out both radio and X-ray pulses, then maybe all other fast radio bursts do that as well. But at those distances of other galaxies, it will be so difficult to see those X-ray flashes.
Sorry, complete this off.
Yeah, and so that's the best analog we have right now for what we think fast radio bursts might be, but it's a very wimpy example if that's the case.
I mean, it's confirmed that the source is a magnetar in this particular case. Can the source be something else, say galactic collisions?
Well, we haven't confirmed that it definitely is a magnetar. What we did find, though, is that was quite interesting to us was that when we went looking at images that we took of the host galaxy with the European Southern Observatory's very large telescope in Chile, when those images came back to us, we noticed that rather than there being just a single galaxy that we could pin this burst to, the galaxy that was closest to the burst location actually had two companion objects that looked quite close together on the sky. But of course, it's possible that some of those might be in the foreground or the background. So to check that, we went back to the very large telescope. We made other observations to measure the redshift or the distances to each of them, and we found they're all pretty much the same distance from Earth. So that suggests that they are close together in space. And most likely, actually, they're in the course of interacting with each other, gravitationally influencing each other, and maybe even in the process of merging, because that's something that lots of galaxies were doing when the universe was half its present age.
Right.
And so that process of merging and interaction, we know that also drives significant amounts of star formation in galaxies. And when you increase the amount of stars being born every year, you inevitably finish up a few million years later with an enhanced rate of supernova explosions, when the most massive of those stars reach the end of their lives, use up their fuel and explode. And one of the things that they would leave behind would be potentially a magnetar. And so this scenario kind of fits the theory that we have for where fast radio bursts come from. It's not conclusive proof that the origin of this particular burst was one of those magnetars. But if, for instance, we'd found the host galaxy for this burst to be a galaxy that wasn't forming stars and apparently hadn't been forming stars for a very long time, that would be evidence perhaps against this magnetar theory. That requires relatively recent supernova explosions.
We know that half of all matter that should be present in the universe is effectively missing. Missing matter, of course, is not the same as dark matter. I want to make that distinction for my viewers. How do FRBs help in establishing how much matter is missing?
Yeah, so that's one of the really neat things about fast radio bursts, is that, as I mentioned earlier, when the pulse travels through space, if it encounters any electrons that are not bound to their parent atoms, perhaps because they're in let's say, a gas which is very, very hot, and so the particles move very fast, the electrons effectively are free to move around by themselves, then for every one of these electrons that the pulse intercepts, that dispersion will be increased by a small amount. And so the more of this ionized material between galaxies that it passes through, the more of that dispersion. So we had realized for quite a while now that when we add up all the stuff around us that we can see, that be stars, dust, cold molecular gas, even and warm neutral hydrogen and so forth, we only ever found about half the total amount of these, what are called baryons, as distinct from dark matter and very distinct from dark energy. But we only see about half of what should be there based on our the Big Bang theory for the origin of the universe. And that was a concern, but there was a theory going around that perhaps where most of the mass actually was contained in stuff between galaxies, and in particular, if this matter was so hot that it might only be visible at X-ray wavelengths. However, because this material is so thinly spread out, it's very, very diffuse. And so it's actually quite difficult to see, even with our best X-ray satellites. Thankfully, though, fast radio bursts turn out to be the ideal probe of this material, because for whatever direction they came from, we can see how many of these free electrons from the hot gas it encountered. And when we compare the amount of these electrons that we've measured to the distance of the host galaxy, we found that the ratio is exactly what was predicted by Big Bang nuclear models for the universe. So in a way, we found that missing matter. We knew it was there all along. It was simply that until fast radio bursts came along, we had no way of directly probing that material, and now we do. And so we're beginning to use these as probes of just how much stuff is out there. And one of the things that we notice is that it's not the same in all directions. In terms of the density of that material, clearly is not uniform. And we kind of expected that too, because we've seen when we map out the distribution of galaxies and gas between the galaxies, it tends to form what's referred to as a cosmic web. Matter very much likes to clump together in long filament arrangements, and that leaves large, relatively empty regions between them called voids. So these fast radio bursts actually turn out to be potentially quite useful for enabling us to map out the density of material around us in 3 dimensions. It's a bit like doing an MRI scan of the inside of your body, except here we're doing measuring the structure of the material between galaxies, which to me is just incredible that we can do so much with an object which we don't even understand what causes them.
Absolutely, yeah. You know, one of the major implications of FRBs is that we will be able to actually weigh the universe. Tell me about that. How does that work?
Yeah, so this comes back to the missing matter story, in the sense that once we've worked out how many electrons are along our line of sight for a particular burst, we compare that to the distance that we measured to its host galaxy with our optical telescopes, and that in effect gives us a density of material between us and them, and then we just apply, knowing what the volume of space would be, we can then work out what the total mass of material that wasn't previously seen is. And so this is, in a way, we talk about weighing the universe, perhaps that's not the most appropriate term, but it's certainly accounting for nearly all of the mass that was previously missing. But as I've said, it was more a case that we weren't looking at it in the right way.
Right. I read as part of your story that as few FRBs as half a dozen could help determine the density of the universe, and hence the missing baryonic matter. Would you care to elaborate on that a bit?
Well, I think I've kind of addressed that already in the previous.
Yeah, you did. Yeah. Okay. No, that part, but I'm trying to get a handle myself on about the density part. Maybe it gets too technical beyond a point for the viewers.
No, not necessarily. It's just as I said, but we derive that density by comparing the amount of ionized material that we measure from the fast radio burst signal And we compare that to the distance of the host galaxy, and that gives us an average density of material along that line of sight. But then, since we know the distance, we simply scale that up by the volume of space that it would have travelled through, and that gives us a total mass equivalent. And then, in effect, then that's how we weigh the universe that way.
The science of FRBs is barely 16 years old. The first FRB being discovered in 2007, I think. How do you think the emergence of AI could help you in advancing the science now?
Yeah, that's true. We only had the technology really for the last 15 to 20 years to do the searches at the very high rates that are necessary to find these objects. At the moment, I guess we tend to use a bit of a blunt force approach to finding these bursts, in the sense that because we don't know where or when the burst is going to come from, we have to be constantly searching through the data, well, not we, but our computers, searching the data, looking for a signal which is stretched out in the characteristic way that a fast radio burst would be. And all the time we have to filter out things like radio interference, and that can be everything from mobile phones to low Earth orbit satellite constellations, can all put out signals, although generally they don't show any of this dispersion. The pulse arrives at all the frequencies at pretty much the same time, so we can kind of ignore those. But because we don't know how much dispersion the next burst is going to suffer from, we have to run these constant iterative searches, trying all possible different values of dispersion until we find one that sort of matches. But there are now attempts being made, now that we're getting good at knowing what these signals typically look like, and we can even predict for a given sight line what the most likely dispersion value might be, given other measurements of the distribution of galaxies in that direction. And so we are on the cusp now of beginning to apply machine learning methods to try and save us some time, possibly get better at finding objects that previously would have been eliminated by our searches. But at the moment, we're still somewhat reliant on our more traditional searching methods.
In this context, how do you see the James Webb Telescope? Because what James Webb Telescope is finding is all kinds of challenges to the prevailing theories, including perhaps the age of the universe. How do you think JWST can help in your particular field?
Well, it's funny you should ask that, because just a few hours ago, we submitted our very first proposal for observing time on the James Webb Space Telescope to follow up on a different one of our fast radio bursts. This is one that, again, has a very high dispersion. It's actually about as high as the burst that we just published last week. The problem with that one is that when we went looking for its host galaxy with our ground-based telescopes, we couldn't see anything. There's just no sign of it. And that's a problem, because without knowing where that host galaxy is exactly, we can't get a measurement for its distance or redshift, because we don't know where to point our telescopes. So what we think, though, is that either this is the most distant fast radio burst ever, even more distant than the one we've just published, and that will push the host galaxy way beyond the horizon of our current ground-based telescopes, or possibly it might be at a distance even less than the one that we've just found, but its host galaxy may be much, much fainter than any host galaxy for a fast radio burst that we've found so far. So either one of those would be a pretty significant outcome, and we've tried on multiple occasions to get observing time on telescopes here on Earth to try and get to the bottom of that, and we haven't succeeded yet. So we've decided to go for broke and make use of the fantastic capabilities of the James Webb Space Telescope. We've run our numbers, and we think that in just less than 10 hours of observing time, there's a good prospect that the James Webb Space Telescope would be able to not just take a picture and show us the location of the host galaxy, but then we'll be able to follow that up with getting a redshift measurement as well for that one, and hopefully confirm that perhaps it is the most distant one ever, or maybe if it is a lot closer, then certainly the host galaxy in this case just turns out to be really, really faint. But we won't know for several weeks whether that proposal or request for time has been successful, because the James Webb Space Telescope is one of the most highly oversubscribed, a very, very popular telescope, as you can imagine. And then even if we do get the observing time, it'll probably be a few more months after that before they're able to take the data for us. But we're certainly looking forward to being able to put James Webb Space Telescope to the test and show just how useful it can be for not just understanding the very distant, very young universe, or looking for planets around other stars, but also when it comes to making really useful contributions in the fast-growing field of fast radio burst research.
Just last couple of things. One is about this particular FRB. I'm curious in terms of what exactly do you see? Do you see, is it a visual representation? Do you see, I'm curious to find out what tells you that this is it.
Yeah, so once the computer algorithms are searching the data stream coming from the Australian Square Kilometre Array Pathfinder telescope, whenever it thinks it's found something of interest, it will send an alert by email and other messaging channels to our collaboration, which is primarily made up of astronomers here in Australia, but also has people in the US and in Chile involved. And it will show us not just the coordinates, rough coordinates in space where the object came from, but it will show us this plot of the arrival time of the pulse as a function of the frequency. And that's a good visual check for us to go, yep, no, we see that to us is what a fast radio burst should look like. It will also then show us what the pulse would be if we correct for that dispersion. So having measured how much stretching there is, again, in proportion to the amount of these electrons that it passed by, it will then try and shift everything back to the same arrival time. And that will give us an idea of what the pulse original pulse shape was, how spread out it was, whether it was less than a millisecond in duration or maybe several milliseconds in some cases. And so that gives us an idea then of whether a good indication of whether the burst is probably real. We then have another system that takes the data stream coming off the telescope and captures only the last few seconds of that. And then we store that on a separate external hard drive. And later on, within the next 24 hours or so, we can make an image at radio wavelengths of that field and see just exactly where in space that burst was to a fraction of an arc second. So that's 1/2000th the diameter of a full moon. But that's the level of precision that we need in order to be able to pin down which of the billions of galaxies that we see at optical images across the sky, which particular galaxy it most likely came from. And then we can send those coordinates to the telescopes in Chile, and they go ahead and get the better quality images of that host galaxy. And ultimately, they get a spectrum for us. And from that, we can measure the redshift, the distance to the host galaxy.
And to conclude on a non-science question, I always ask this question of physicists, especially, and people who work in your line of work. How do you deal with mundane stuff once you're dealing with the kind of distances, the scale of the universe on a daily basis? When it comes to home, domestic stuff, human relations, how do you manage that? Isn't that too trivial for you beyond after a certain point?
Not really, no. I mean, even for astronomers, it's hard to get your head around what 8 billion years really looks like or feels like, right? So at the end, you have to treat it as a number, or in some cases, we just add it to our plots of dispersion measure versus redshift and so forth, and we go, that's nice. Now, I wonder what's for dinner. So we still have to go about our regular daily business. But for me, it's that sense of discovery, of just not knowing. Like this morning, I could have woken up, and before I went online to speak to you, there might have been another alert from our ASCAP radio telescope in Western Australia to say, hey, check this out. We go, hang on, there's another. In fact, that one has a really high dispersion. That might be even more distant. And so it's just that sense of anticipation that's one of the things that sort of gets you out of bed every morning, no matter what else is going on in the world. It's nice to know that there are still things out there that we haven't fully appreciated, and we don't yet know when and where the next most intriguing fast radio burst will come from, but chances are it's already on its way here. And it would be a shame if we weren't alert and listening for these bursts. But as I say, it's something that we've only been able to do for the last 5 years and with our system. And the whole field of fast radio bursts didn't exist 20 years ago. That to me is just remarkable. The textbooks that I used as an undergraduate astronomer, there was no section in the index marked fast radio bursts. That's how fast
that's amazing.
Changes.
You are at the frontier of the science.
We believe so, yes, although there is competition out there, of course. Other we're not the only group to have recognised that fast radio bursts are the future. And so there are collaborations in Canada and the USA and in Asia now that are building telescope arrays dedicated specifically to finding more fast radio bursts. So we don't have the field entirely to ourselves. For now, at least, we hold that distance or age record, but I suspect it won't be long before someone else breaks that. But we're not resting on our laurels, as I say, with upgrading and enhancing our own systems. And so we do plan to remain, hopefully, at the cutting edge for quite some time yet.